So what we're going to do now is start to look at the different types of chromatography. First type we're going to look at is called thin layer chromatography, or TLC. And this is also, pay attention, this is also a required A-level practical. This is required practical 12. So you will need to be able to describe the method and explain the results and the process involved in this technique. So this is used for checking purity. So you maybe have made a chemical in a process, maybe you've made some aspirin, and you want to check that you only have aspirin present and none of the other things that you used to make it are still there. Or to identify components in a mixture. So maybe you've hydrolyzed a protein and you want to know which amino acids were there. Now it's essential for all of these types of technique that you can tell the examiner what the stationary phase is and what the mobile phase is. So in thin layer chromatography, at GCSE you might have used a piece of paper, but at A level we're going to use a thin layer, that's where the word thin layer comes from, of solid, and then we've got two chemicals we often use, silica, SiO2, or alumina, Al2O3, aluminium oxide, on an inert and unreactive solid support. Now that solid support might be a piece of glass, a piece of metal, it might be a piece of plastic. So let's just have a look. Remember that the key word here is stationary phase. What is the stationary phase? Well, it's a thin layer of solid. What's our mobile phase? Well, we put our plate into a small amount of a solvent. That solvent might be water, more likely to be something containing maybe an alcohol. And that solvent is going to move up the plate. So our phase is a liquid. So our mobile phase is a liquid and our stationary phase is a solid in TLC. So how do we do it then? So here's a picture of the experiment. So let's just have a look at the things we've got. So this is our chromatography plate. This is our piece of glass or plastic coated in the solid. So that's coated in our solid stationary phase, so our SiO2 maybe, it's the normal one. And SiO2 is very polar, so things that are polar may well stick better to it. We're going to put it into our beaker. We're going to draw a pencil line. It must be in pencil. Remember that if you were to use pen, the pen would run. And we're going to draw that a short distance from the bottom. And we're going to make sure that when we put our solvent, which is our moving phase, in, it is below the line. Otherwise, all your sample is just going to dissolve straight into your solvent. It's just all the things that you've put on that pencil line are just going to drop off and into the liquid at the bottom. We're going to put on a lid. Okay, this is going to prevent evaporation of your solvent. And it's going to create a saturated environment. So the air in that beaker is damp, like going into a room with lots of laundry hanging up. You might even sometimes find that somebody puts in a piece of filter paper at the back to help saturate the environment. Keeps the whole area around the plate saturated in solvent, and so the solvent can rise up more easily. When the solvent has risen up, you will get a line at the top, and we call that the line that the solvent moved to, the solvent front. And then we can see that we spotted our samples onto these little dots here, and we can see where they've moved to during the process. So this would have happened over a period of time. It wouldn't look like that when you put it in. So what do? We've made some aspirin perhaps. We need to dissolve that aspirin into some solvent so that it is a solution so that we can spot it onto our plate. You're going to draw a pencil line a short distance from the bottom. Remember that it's pencil because pen would run. We're going to place a small spot of our sample onto that pencil line and allow it to dry. And we're going to place that TLC plate in a beaker containing a small amount of the solvent. We need to remember that the bottom of the plate must be in the solvent, but the solvent must be below the line. So I'm just going to write that in. Okay. We're then going to cover that beaker with a lid, and we're going to allow the solvent to rise. Now once the solvent has risen to almost the top, so you do need to watch this, you need to not let the solvent rise right to the top. It could take the spots off the plate with it if you leave it there too long. Once the solvent has risen almost to the top, you're going to lift it out and mark the solvent front. So immediately while it's still damp, you need to mark where that solvent got to. The whole time that you handle a TLC plate, you must be wearing gloves because your fingers contain chemical, the oils on your skin contain chemicals that will contaminate the plate. So you really must make sure you're wearing gloves the whole time. And then once you've done that, you let it dry, and you're going to use some sort of locating agent to find the components, to see the spots, because most chemicals are colourless, so very difficult to see. So what are our locating agents? So some common locating agents are ninhydrin, which is really good for locating amino acids. So we'll come across that again in the course later. UV light, if your compounds are UV active, they'll show up in UV light, or if they react with iodine, or maybe even something like potassium permanganate, they may react and that will help them show up. So how is your TLC separating your components? So what you remember, you've got your solid support at the back, and then this is your solid stationary phase, which is your thin layer of silica. You've drawn your pencil line near the bottom and you've put your spot on, and then you've put it into your solvent, and the solvent is the mobile phase. It's moving up the plate and it's carrying the spots up with it. So which of those components is the most soluble in our moving phase? So this one is the most soluble because it's moved the furthest. Remember, it's a balance between solubility in the moving phase and retention by the stationary phase. And this one is the greatest retention by the stationary phase because it's moved the least. So it's the least soluble, if you wanted to think of it that way, or the most retained, whereas the one at the top is the most soluble in the moving phase or the least retained by the stationary phase. Each component has a different balance in this between these two factors, and the distance moved by a particular component is going to be expressed as a fraction of the distance moved by the solvent. It's going to be a value for the spot over a value for the solvent, and that is called the RF value. And the RF value for component is always the same for a particular combination of stationary phase and moving phase. So even if you were to leave it for longer and get a bigger plate, if you've used the same stationary phase and the same moving phase, it might be different actual distances, but the fraction will remain the same on whichever material, whichever plate you're measuring, as long as it's the same sort of plate, the same chemicals on the plate and the same chemical in the solvent.